All right. Hello, everybody. Welcome to our Robotics Pathways and Career Speaker Series. I'm Professor Chad Jenkins. I'm the Associate Chair. I'm an Associate Chair of the Robotics Department here. I'm also the Undergraduate Program Chair. And here's a quick question I just want to ask for everybody. When people learn that there was a robotics major at Michigan, what's the first question that they ask? The question we get the most? Yeah, what? Okay, that's not on the highest on the list, but I can tell you, yes, you can probably fit it in depending on what courses you've taken, which is why Kayla over here, Kayla, our fabulous undergraduate coordinator, can help you set an advising meeting so we can figure out a way for you to do that. But let's say that's, if we're playing the Family Feud, that would be sort of like, that would sort of be lower on the list. That might be answer number 5 or 6. Yeah. What can I do with the robotics major? Everybody asked that. And so while I have many great answers for why that is, why you want to do it, salary, job satisfaction, impact on the world, what we found is the best way to actually do it is to bring in awesome people who are leading roboticists in the field to give you examples to show you what you could do as a roboticist. And this is the first time we're offering a robotics major. So it's really something special. Our faculty, our students, our staff who are all involved, we're all trailblazing and doing new things. This is a new endeavor to help define the discipline of robotics. So we're really excited to have you here. And in particular, we're really excited to have Dr. Kimberly Hambuchen from NASA Johnson Space Center joining us, and she is our speaker for tonight. Wait, I'm gonna dig up a little information here on Kim. So fun fact is Dr. Hambuchen and I, we graduated, we both got our PhDs the same year. I went off into academia and I followed the faculty path. Kim took a job at NASA, so she's been at Johnson Space Center, and she's worked her way up so that she is now the acting deputy of the International Space Station Systems Engineering and Integration Office down in Houston, and so doing a number of wonderful things that she'll talk about with that. But Kim has worked on a number of great robots down there, such as the NASA Robonaut, the Valkyrie system. Really, they do amazing things down there. It's one of the few buildings that I get jealous of when I compare it to the robotics building we have here at Michigan. Both are amazing places. Just to let you know that Kim is going to talk about a number of these things, but the internet also says that she grew up in Conway, Arkansas, which is pretty cool, and that she also likes to make jewelry, and she likes to lie on the beach, and she likes renovating her house, and so there's so it's not all work and no play for roboticists. So just some examples of that. We also have a number of great speakers that are coming up for the remainder of the semester. We're going to have Bruce Huang from Google, who's going to talk. All of our remaining speakers are alumni of Michigan. So we have Bruce Huang from Google. Then we're going to have Shiva Ghosh, who's at NVIDIA Corporation, who's going to speak 2 weeks after that. And then our final speaker for this semester will be Zhen Zhang, who's at JP Morgan. So with that, I think we have a great lead-in for our fabulous speaker tonight. I'm going to give the mic I'm going to pass it over to Kim, who's going to give you a little bit of insight about her pathway into the field of robotics. So Dr. Hambuchen, thank you for joining us.
You're welcome. Thank you for having me. Okay, so this is not my normal robotics talk that I tend to give. I was talking to Chad about, how this should be laid out, and realized that it's the kind of talk that I would love to give over and over, because I love talking about how I got to where I am and explaining to people that it wasn't a perfect linear path and it wasn't a streamlined road. So, but I also get to intersperse it with all of the things that I've done over the years that have gotten me to this point. So I guess it means I'm excited to talk about myself, which sounds really narcissistic, and usually I don't like to do that. So what I'd like to point out right now is I have a title on my slide that is crossed out because I was the chief of the Robotic Systems Technology Branch down here at Johnson Space Center. And very recently, this summer, was asked to do something we call a rotation, which is essentially you go move to another organization for a period of time. And that rotation happens to be in the International Space Station, which has been phenomenal so far. So, but my background has always been in robotics up until recently. So, okay, there we go. This video is essentially why I came to NASA. I will say back in the day when Chad and I were finishing our degrees, there weren't a whole lot of opportunities for someone who had focused in robotics from grad school. Essentially, you went into academia like Chad did. You went to work for Department of Defense like many other people have done, or you went to work for NASA. So I chose NASA. And this is a video of one of our star robots, Robonaut 2, up on the International Space Station doing what we like to call a Saturday morning chore. It's essentially pulling out a hand wipe, and then it will wipe down a handrail, which is one of the astronauts' chores on the space station. And this was really just a test for us to see if a robot could do something that the astronauts do inside of the space station. And of course, it's slow. It isn't very accurate. And quite honestly, behind the scenes, there is a lot going on in our little Robonaut mission control room to make this happen. And there was a lot of work before to make it happen. But this was kind of the ultimate for us in my branch, actually getting a robot onto space station and demonstrating that it can do something useful. So I like to think that this is a pretty cool video, robot in space doing things. And it's actually pushed us to want to do quite a bit more with robots in space. So my background, like Chad said, I can't believe he pulled out Conway, Arkansas. I grew up in a tiny town in Arkansas and had the good fortune to know what engineering was before I applied to colleges. So I did end up going to Vanderbilt University. And I imagine we've got some undergrads in the audience today. So I just want to tell you a little story. I started with a biomedical engineering degree, and we had to take several electrical engineering classes. And I withdrew from the very first intro to electrical engineering class because I didn't know what was going on. And the next semester I took it again, and I really I couldn't grasp it, and was talking to the professor who happened to be the chair of the department. And I told her, I said, I think I just need to drop engineering as a major and do something else. And she said, no, you're not going to do that. And in fact, you're going to add an electrical engineering major to your degree. So she managed to talk me into doing a double biomedical engineering and electrical engineering major. And turns out that was a really good thing. I eventually did figure out the electrical engineering, but I had to add 6 more hours to get the double degree. So I ended up doing these independent studies in image processing and computer vision. And the computer vision one I was doing in Vanderbilt's robotics lab. I didn't know anything about robots. I didn't know it was a field you could study. I just fell backwards into it, and turned out that was pretty interesting. I mean, robots, you're all here at this, so I imagine you have some interest in robots. So when I went to grad school, robotics was one of the areas I thought maybe I'd go ahead and focus on. And I did end up staying at Vanderbilt for my master's and PhD. And I will tell everyone in the audience, don't do that. You'd like to get a little variety. I had my reasons, and those reasons don't exist anymore. So I worked in the dexterous robotics lab at Vanderbilt, getting my PhD in electrical engineering. And I had the fortune, I mean, a lot of things are just luck of the draw. My advisor was part of a kind of consortium of academics led by Rob Ambrose and Bob Savely down at Johnson Space Center, who Rob Ambrose was running the Robonaut lab at Johnson. And Chad's advisor happened to be part of this consortium too, which is how we both met. And so I actually got to start testing out my thesis work on Robonaut at NASA, which was pretty cool. I also ended up getting a graduate student researchers fellowship because of this consortium. So I got to spend summers at NASA. And I mean, that's a pretty cool thing to a young grad student. So I decided, okay, this is really interesting. Space robotics, working for NASA. That's something that I think I want to do. So lo and behold, I discovered that NASA had a postdoc opportunity. And Rob Ambrose, who eventually became my boss and now has left us and gone to Texas A&M, he had funding for it. And so I became a postdoc at NASA. Oh, and that picture on the right that Chad insisted I put in this presentation, that's me with my robot Isaac in grad school. And I'm sure it looks familiar to some of, if we've got any grad students in the class or in the series right now, because you've got brightly colored objects that are very distinguishable from the black background. Anyway, so I went on and did my NASA postdoc, and again, I got very lucky, and a hiring position opened up within the division I work in, and I got hired on as a federal employee. So I had a lot of, luck throughout my schooling, but I also, worked hard and chose the path that didn't seem like the easiest path. So that's kind of how I ended up. Well, that's how I ended up at NASA. And now, well, first, let me tell you about this. So most people probably don't know about a lot of the robotics development we do here at Johnson. Everybody thinks everybody probably still thinks we just run space shuttle, which we haven't done for many years. But we don't do Mars rovers. We don't do a lot of things that you'll hear about, like something going to Europa or Venus. We really do, in my branch specifically, robotic technology development for future space missions. And we focus at Johnson on human robotic systems. Whereas JPL, Jet Propulsion Lab out in California, focuses on science missions. And then we've got Ames Research Center, also in California, that focuses on more autonomy for robotics and systems. So we really have this human component in the technology work we do. And another one of the robotic systems that is managed by JSC are the robotic arms on the International Space Station. Again, that's not what my branch does. We do technology development. So I just kind of want to put that out there so y'all understand the type of robotics that I'm going to be talking about through this. So I'm going to tell you the story of my career journey through robots, which is pretty cool to sit here and say. This is actually a picture. We were fortunate enough to have almost every robot that my branch has ever developed in one place at one time before we sent off some Valkyries, I think. So we gathered them all together for, a class picture. And you see a lot of hardware there. My focus throughout my career has been in software. So for all you hardware folks in the audience, I'm not really going to talk about how we designed and built these creatures, but I'm going to talk about the types of software that I developed for these robots. So when I came to NASA as a postdoc.
Kim, can I stop you real quick?
Oh, sure.
Can you say a little bit about that vehicle that the Valkyrie is sitting on?
Oh, I can. I can't talk much about it.
Right.
That is the modular robotic vehicle. It is a small, kind of car-like vehicle. It is something we developed after the very large rovers that you see in the back here. These are our space exploration vehicles. The mechanical and electrical engineers developed what we call wheel modules for these vehicles. So each wheel, which you kind of can't see very well. Let's see, this thing right here is a wheel module. They're all independent, and power and data all go to each individual wheel module. So they're controlled individually. And what it means is that if you have a wheel module that stops functioning, we simply pick that up and then we keep driving. Unlike your car, which if you've got something wacky going on with one of your wheels, you take it into the garage and get it fixed. So we were working with a commercial partner. They were interested in that concept, and we put the same concept onto the MRV, mobile robotic vehicle. So each of these, we call them e-corners, I think. These are all independently driven and have all of the power and data just come through a cable to each of them. And so the motors that control the wheels are all inside that little module. And they each have their own little embedded controller. And then there's an overall larger controller that manages each of the individual embedded controllers.
I just want to add to that Tim hosted me at Johnson Space one time, and I don't know if I can say this, but I got a chance to ride in that.
Oh, yeah,
the coolest car ever, because you don't just go straight and turn, because each of the wheels can be independent. You can you can spin in place, you can drive side to side and do all sorts of things. Blew my mind. And so that thing is really cool.
Well, you can no longer drive it because it crashed into a ditch and it's dead. We were supposed to have 2 fault tolerant operations on it, and it never got completed because our commercial partner pulled out of the project. So we had an issue with the battery management system, and it turns out the battery died on the driver and he went into a ditch.
It's just too much fun. That's what it was. All right, don't let me stop you. I'll let you continue.
Okay. Okay, so I start my career at NASA, and I don't know what I'm doing, but I get thrown into this project. And what we were really interested in looking at was, how do you operate these complex robots over time delays that NASA sees? So time delay here on Earth can mean milliseconds, but time delays for NASA means much larger chunks of time. So for instance, on the moon, we think maybe we will have a 10 to 20 second potential time delay from when a command is sent to something on the surface and when the data comes back to the operator on the ground. So we had our Robonaut 1, which is the robot in the left. And I'll go ahead and play this video. And we wanted to see if we could actually control this robot, supervise this robot over a 2-second time delay. So what we see on the right is Mike Goza is in very old VR and telepresence gear. And he's actually operating what we call like the digital twin of Robonaut in a simulation. And we had software that was watching what he was doing in this digital twin and trying to predict the intent that he had. So we had certain tasks you could do. You could pick up a handrail, you could push that red button, and the software was predicting what he was reaching for based on his hand motion, where his arm was going, and would go ahead and kick off a command to the robot. Okay, we think he's going for the left handrail. To remove it, robot, go ahead and do that. So this was, very cool to my little 30-year-old brain. And it really got me started me thinking about, this is an interesting topic. This is something that isn't really covered much, because on Earth, you don't have these kinds of time delays, but we will need more and more complex robots as we move further out in our exploration goals at NASA. And we're most likely going to have people on Earth at mission control overseeing these things. So this work kind of defines the rest of my career trajectory, I think. And the most interesting part of this was that it was a collaborative effort between a team at Jet Propulsion Lab and the Ames Research Center and us. And we all started working together. So I got to go out to those 2 centers and meet lots of new people in robotics that I didn't know, and get to do some really interesting work, testing things out, and then getting a paper out of it that I got to go present at Humanoids. And Chad was at Humanoids that year. That was when it was in Genoa. You remember that?
Absolutely. I absolutely remember that.
Yeah.
And I remember I was late for a session and you were like, Chad, you have to get to that session. Aren't you late? And I was like, yeah. And then I ran over and I still was able to chair that session, but I have Kim to thanks for
Oh, okay. I
for
don't
being
remember
my wingman.
Okay, so did this work in intent prediction on a humanoid robot. And then at some point we started working on Robonaut 2 and rovers. So our team kind of got split into these two different groups, and I got put on the rover team. And once again, we're asked to supervise these robots over ever increasing time delays. So it's a little bit easier with a rover that's on a surface, but Rob Burridge and I we developed this, we call it PIGGY, Predictive Interactive Graphical Interface. And it was this system that allowed us to send multiple different commands, to the large rover, which could be driven by humans, but was also a robot. It had control system on it and it had sensors on it to attempt to avoid obstacles. And what we did was we were giving the robot waypoints where to go. So on the left, you see the only camera I had as I'm supervising this vehicle. And then on the right it's actually an overhead map. If you zoom out, it's a DEM of the surface of Black Point lava flow in Arizona, where we went to do field testing. So I could zoom out and I could drop a lot of waypoints into this map and tell the robot, these are the places we want you to go to do some scouting, maybe do some sample collection at some point. And then we had a model of the autonomous trajectory generation within, again, kind of a digital twin, but we never called it that. So we were predicting what the rover would actually be doing on the surface and where it would be driving. And this let us cover a lot of ground. It was, we weren't predicting intent, so it was quite a bit easier, but we started testing this with up to, I think, a 100-second round trip time delay. So I'd send a bunch of commands. These are the waypoints we need you to go to. And then many seconds later, minutes later, we'd get the data of where it was going. So, this is all old stuff, man. We published this in 2009. So these types of concepts are well worn by this point, but this was all still pretty new, especially because we had this unique situation at NASA that so many other people didn't have. Once again, I'm kind of building my knowledge, starting to gain more experience, now a different type of robot, and using everything I've learned to kind of move into the next role. So the next role was, I was told we're going to take our Centaur 2 robot, which is Robonaut 2 on top of a mobile base, out to the desert, and we're going to demonstrate sample collection. And we're going to have a time delay. And we need you to make that happen. So I'm thinking, okay, how are we going to do this? The intent prediction software, it was interesting. It was a nice little research project, but it didn't really get us. It took a lot more work to make that happen than if we just did what we call bump and wait, which is send a command, wait for the data to come back, and then send another command. So my objective for this, let me go ahead and play that video, was to actually have Robonaut Centaur 2 go find a rock, bend down, pick it up, and then go back to its, the place where it would put that sample. And it was a mishmash, essentially. The interface I used was this mishmash of kind of different pieces of software. Nothing was very coherent. It was very difficult, essentially. And I was like, okay, there's got to be a better way. And this is it picking up the rock. Oh, and by the way, that's a rock that we brought to the desert from our rock yard at Johnson because it fit the hand so well, and I could pick it up every time. And I still have that rock. But this was really this was, I want to say 2012. Well, it was probably 2011 when we did the work. This is kind of what made me go, there's got to be a better way to do this. We can't, we're going to have to operate these robots over time delays. It's just, there's no getting around it. You can't get faster than the speed of light. And then, we're not sending our data as fast as speed of light. So this was kind of the impetus for the next challenge I took on. Okay, I can't see you people in the crowd, so I'm not going to ask, but I'm going to assume a lot of folks have heard about the DARPA Robotics Challenge. It's been almost 10 years now.
How about this? How about this? We'll do a quick show of hands. How many people have heard of the DARPA Robotics Challenge? There we go. I'd say about a third or a quarter of the room.
Oh, okay. Well, then I'm happy I left this slide in. So the DARPA Robotics Challenge was a crazy event that DARPA put on. The trials were in 2013. We actually we proposed to get money from DARPA to build a bipedal humanoid. And our proposal was selected, one of many. And the idea is that there would be this, so I don't really want to get into all of that because I have so many things to talk about, but the idea is that there's a robot, there's a disaster site, and the robot needs to do some things at this disaster site. So let's see, the primary technical goal.
Can I add a little context on that? So this had just happened. This took place just after the Fukushima disaster that happened in Japan, and so lots of people were really thinking about how do we, if there's a disaster area, how can we send robots in to go help, basically turn valves to, to secure certain areas, go drive into certain areas where that might be hazardous for people. And so there was a big challenge to make that happen. You think that's a good summary?
That's a good summary. So it was a 15-month from design of the robot to we're at these competitive trials operating the robot. It was 15 months, which is crazy. We're operating under degraded communication, which means loss of signal sometimes, limited bandwidth, and oh, by the way, probably some latency that would be more like NASA latency than terrestrial latency. So it was really a good challenge for us to push technology that we know we eventually will need. And then I've got a list of the different tasks that we are going to be completing. So, the work that I did with the Centaur 2 robot in the previous movie was just bending over and picking up a rock. Now we're like, how are we going to do all this? Like, how are we going to do this? And Chad thought that we were having the time of our lives, but we were just crazy to think we could do this. And well, we really didn't. We failed miserably at the trials. But I was working with some folks, and through the course of our development on this, we created something called affordance templates. And maybe if some of you in the crowd work in Chad's lab at all, you know what I'm talking about. But essentially these, and we weren't the only ones really who created this. Most everyone came up with their own version of it, but affordance templates allowed us to much more easily supervise complex robots over time delays with bad networks. And you could kind of quickly create a user interface that tells the robot how it needs to interact with something to accomplish a task. That's a really very high level summary. And once again, I was asked to put this video in here. But that's me over there. I can't see the robot, and I'm using affordance templates to operate the robot over time delay. And it actually was much more efficient than what I was using to pick up a rock with Centaur 2 out in the desert. And once again, got a few papers out of this. We created a ROS package, distributed that. And this was also the first time we used ROS on a robot. I believe the Robonaut 2 group was also putting ROS on Robonaut 2 at the same time. But ROS finally allowed us to do a lot more of these robots because we had small teams than we were able to do, and really kind of changed the game for us, at least at NASA, and I think in robotics in general, but that's my opinion. So I actually have a better video of this. This is a little video we made to just demonstrate what they looked like. So once again, we're operating in a virtual world, digital twin, if you will. I don't really think that's what this is. Populating it with the robot sensors, or populating the virtual world with the robot sensors. It allows the user to see where everything is. We're getting a depth map from the LiDAR. And you can see this is an affordance template, this little thing that is, it's actually an RViz marker. And we built off of that, and we could add in, there's the ladder. We could modify it to fit the data that we're seeing. And within these little RViz markers that we're using, we actually encode how the robot could climb a ladder. Granted, we didn't ever climb a ladder with this robot, but if we could have, we could embed that into this marker, and then the robot would know how to use this object that it doesn't really know, it can't see, but we gave it that information. So a lot of this comes from all the frustration that I had through my career in trying to figure out how to operate these robots over time delay. And once I did this, we failed at the DRC trials. I was asked by the Robonaut 2 team, could you please put this on our robot so that we can use it, because we need something like this to operate the robot on space station. So I got to go port the code to work on Robonaut 2, which actually was pretty easy because of ROS. And that became the main mode of operation for Robonaut 2. The videos you're seeing, just a little explanation here, is Robonaut 2 in its, we have a space station mock-up inside of something called the Active Response Gravity Offload System, which is like a gravity simulator. It can actually offload anything in all all 3 directions and 3 attitudes. And this is in a microgravity simulation because at the time, the Robonaut that was on space station had stopped working, and we had a problem with it. And so we couldn't do testing up on space station. So we did it on the ground in a zero gravity environment. But so finally, I'm at the point in my career where something I've done is getting used by someone else. I have a lot of, and this is something you guys need to learn, I have a lot of young employees who get very frustrated when the work they've done ends up not going anywhere. And I'm like, guys, let me tell you, I mean, Piggy is sitting on a server somewhere doing nothing. You know, the intent prediction sitting on a server. I don't even know if that server exists anymore. But eventually got some work done that then started getting picked up and used. Chad and I, we did a hackathon, maybe? I don't know. It's been a while. With affordance templates, and Steve Hart, my affordance template partner. So, and we've had other grad students pick it up and do a lot of really interesting things with it. So this was pretty cool. But you know, when was this? This was probably what, 2014, 2015, when I'm finally getting it on Robonaut 2. And so that's a good 10 years of my career where I finally get to the point where something is useful. So just bear that in mind if as you go through a robotics career. And then, oh, this is another example of, this was kind of the last project that I was overseeing before I went and became the principal technologist for robotics at NASA headquarters. And they took affordance templates and started using it. This is really cool though. This is, the focus of this project was to create autonomous task planning at a high level. So the robot's actually determining, it knows what it needs to do. It's got this plan in PDDL, if anyone knows planning. And and it's got time constraints. And we essentially mocked up a robot working with a freezer payload on space station. And so it's got to make sure it gets something out of the freezer at a specific time and puts it in the right place and lets it sit there. And, but they used affordance templates as their kind of operations tool. So that was really exciting for me. Okay, so like I said, that was the last project I was overseeing. Then I went and became a Principal Technologist for Robotics. And then I became the branch chief for the branch that does all of this work. And that's been my career in robotics. So I want to talk a little bit about robotics at NASA. If anybody's interested in maybe a future career, what I really wanted to focus on is this operations versus technology development. So on the left, I hope it's your left, you'll see this is the space station arms. So it's, what are they called? Oh, Canada Arm is probably what you would know that as, and then Dexter, which is kind of a dual armed, kind of like a gripper, if you will. And we run these out of Johnson Space Center, and this is solely an operations project. On the right, you've got Robonaut 2, and this is solely a technology development project. Just FYI, Robonaut 2 was not originally designed for space station. We were asked to put it up there after it was designed and built. So we don't think that a very large hulking platform is appropriate for the space station. But, you know, you've got the space station arm doing things. It's heavy operations most of the time. And then you've got Mars rovers out there doing science and trying to figure out if there was life on Mars. But then there's this technology development area. So I just kind of wanted to point out there's so much that we still need to be doing at NASA. And so we need a lot of young blood and bright robotics engineers to help us. And these are kind of the three areas that I really focus on when I give talks like this. In space systems, we're really starting to look at building stations and arrays in space because it's very difficult. We can't, you know, we're limited by what we can put into a carrier, a vehicle that gets launched from Earth. But if you get multiple pieces of things up in space, you can assemble them, or you could start manufacturing things in space. Surface systems, lots of exploration, collecting samples, in situ resource utilization, otherwise known as ISRU. That's actually living off of the surface of whatever you're on. How can we use lunar regolith to create oxygen for astronauts? Surface construction, which should be obvious, constructing things on the surface. And then there's all this human assistance. How do you create a robotic assistant that an astronaut will trust? It's very difficult. Astronauts can be stubborn. And, you know, basically, how do you have a robot that can take care of human environments, maybe when astronauts aren't there? So we have lots of different areas that we're looking into. One thing I do want to emphasize is commercial space is a thing now. SpaceX kind of changed the game. So, and we're starting to see a lot of startups in space technology, and robotics is one of those areas. So whereas 20 years ago, I couldn't have gotten a job at a space robotics company because they didn't exist. Now there's a lot of them. And they're working with Blue Origin, and they're working with NASA, and they're working with Axiom, and there's just a lot of commercial space going on. So I don't know how much of this type of technology development will continue to be done here at NASA. NASA is really pivoting to buying services from providers. And so if space robotics becomes a viable commercial venture, then I think we'll start to see a lot of companies that are doing that work. So that's just something I wanted to kind of let you know about. And then Artemis is our current mission goal. So we're planning on returning to the moon. And that is really to figure out how to get to Mars, or how to live on Mars. So you can see there's actually a lot of little robotic systems down here. We're building some, let's see. One of these is our Viper rover. I'm not sure which. We've got the human rovers. So there's still a lot going on. But just, you know, I don't know what's going to be NASA developed, what's going to be commercial space developed. Okay, but what I wanted to end this with is I've done all these things. I've been in robotics, and I've always been the robot girl, you know, the robot chick, as I was telling my friends. But I moved into this position in the space station program, and I'm learning something new almost every day. It's very cool. I did not realize I would love it this much. I kind of would just love to talk about space station for an hour. But I had no idea that the path I started back in, you know, gosh, undergraduate would lead me to here. And it was unexpected that I'm doing the space station thing, and it's really exciting. And so just, you know that robotics can actually lead you to a bunch of places that you might never have expected. So with that, I believe I'm done with my presentation, Chad.
All right, let's thank Dr. Hambuchen.